Hi, and welcome to this video, which is the last one where we're going to be looking at the normal distribution. And in this one, we're going to be looking at specific use of the normal distribution, which is as a way to find an approximation to binomial distributions. Right, so here we go. We're going to use the normal distribution as an approximation for the binomial. What's going on? Well, if we consider certain binomial distributions with certain parameters, they've got a similar shape to a normal distribution. So let's have a little look at this one. We've got x, our random variable, is distributed, it's binomial, and we've got 40 trials and the probability of success in each trial is 0.5. And what you end up with is a distribution that looks like that. It's symmetrical, the mean, the median, the mode are the same, and you can see if I overlay a normal distribution curve over the top of it, they're looking pretty much the same shape. So this will work for certain binomials, but not all of them. What we need is certain characteristics, and essentially we need n to be large, and it's normally more than 30. We need a value of p, our probability of success close to 0.5. It's the value of p that starts skewing it. So if I had values of p, for example, maybe 0.8, 0.9, that would cause this distribution here to skew to the right. If our value of p was maybe 0.1, we'd be more likely then to get smaller values, so our distribution would be skewed to the left. But when you've got a value of p close to 0.5, it's reasonably symmetrical. Now, there's no hard and fast rules, but again, if you're being asked in the exam about whether or not it's appropriate to use normal to approximate a binomial, just look out for those two key things and make comments upon them. So what we're going to do is we're going to take our binomial distribution, our random variable is x, and we're going to come up with another random variable y, which is going to be our approximating distribution, and that's normally distributed with mu and sigma squared. And what we've got is mu, the mean of a binomial distribution is n times p, so that's the number of trials times by the probability of success. And as it turns out, the variance for a binomial distribution is n times p times q. So we've got mean and variance, so those are the two parameters that I'm looking for to be able to use in my approximating normal distribution. Okay, the other fairly major issue that we've got is the fact that a binomial distribution is discrete. It can only take certain values, whereas the normal distribution is continuous. It can take absolutely any value whatsoever, so they are characteristically very different things. So what we've got to do is make an adjustment for that. The key example would be, for example, in a binomial, you could work out the probability of getting a particular value. What's the probability that x is 2? Probability that x is 3, or whatever it is. You can't do that with a normal, so how do we get around it? Well, we use what's called a continuity correction. So here's my table. So let's say I want to do some calculations. I'm doing some calculations, and I want to find the probability from a binomial that x is specifically 5. But I'm going to do it by using a normal approximation. What values do I use? Well, what I do is I use those values there. So what I'm doing essentially is find the probabilities of any value that will add to make, that will round, not add, to make 5. So anything between 4.5 and 5.5. And again, remember, we don't have to worry too much about what's going on in the inequality signs. It's like a less than symbol or an equal to or less than symbol as far as the normal is concerned, are basically the same thing. That absolutely cannot be said for the binomial distribution. For the binomial, you have to be very careful with your inequality signs. But let's carry on. Let's have a look at the next one. We want the probability that x is equal to or less than 8. So 8 needs to be included. So we need to do anything that would round to 8 and anything down. So that's why I'm going x less than 8.5. If I wanted the probability of the next one, which is x equal greater than x just greater than 3. 3 is not included. So I want anywhere from 3.5 upwards, because the first value that would be included in this one for the binomial would be x equals 4. So values that round to 3 shouldn't be included, and I've just kind of game away a little bit with this one. This thing here, probability x equal greater than 4, that would be exactly the same thing, because for the binomial, x greater than 3 and probability x equal greater than 4 mean exactly the same thing. Finally, what I've got with this one, probability that x is greater than 12 but equal to or less than 20. So we don't want 12 included, so I'm going greater than 12.5. But we do want 20 included, so that's why I'm going less than 20.5. So that's how we get around the whole issue of discrete and continuous. let's have a look now at how we can do a calculation about everything we've been talking about. So what we've got is a random variable. X is distributed binomially. It's got 80 trials, n is 80, and the probability of success is 0.45. So we're going to use a suitable approximation. So the first thing I'm going to do is say, well, yeah, it's appropriate to use the normal as an approximation because n is large and p is close to 0.5. Then I'm going to decide what my normal distribution is going to be that I'm going to approximate it. So there we've got mean and variance. So what we've got is those two values there. So that's n times p is 36, n times p times q 19.8. And so on we go. Let's find the probability that x is greater than 42. So now I'm thinking about my binomial values. The first thing I'm going to do is to convert that into a y value. So using continuity correction, we're going to be calculating 42.5, greater than 42.5. And so grab the calculator, bearing in mind, of course, your your value for sigma, the standard deviation, will be the square root of 19.8. And there we go. There's our value. Now, if we did the calculation as well using a binomial, what we'd end up with is a value of 0.724. So that's a pretty good approximation. Right, on we go. Next one, part B, probability that x is greater than 35 or equal to or less than 55. So we need to apply our continuity correction and think about what values we're using for y. And so we're going to be using greater than 35.5 because 35 is not included, but 55 is, so we need to go less than 55.5. Bang the numbers into the calculator, and there you go, there's your answer. And then finally, probability that x equals 40. So if we want a specific value, we're going to have to go here, 39.5 to 40.5, and we get a value of 0.5983, and there you go.